For decades, returning humans to the moon felt like a forgotten promise, a bold achievement locked in history books, never to be repeated. But today, one of the most expensive and controversial rockets ever built is preparing to rewrite that story. NASA placed a $23 billion bet on a single machine designed to do what no rocket has done since Apollo, and go even further. This machine is the Space Launch System, or SLS. Critics call it outdated, overpriced, and unnecessary. Supporters say it is the only rocket capable of opening the next era of deep space exploration. So why did NASA build it this way? Why reuse decades-old technology instead of starting from scratch? And what makes the SLS absolutely critical to humanity's return to the moon, and eventually Mars? The story of the Space Launch System begins with an ending. In 2011, the Space Shuttle program was retired, closing a chapter that had defined American spaceflight for 3 decades. While the shuttle was versatile, it was never designed to take humans beyond low Earth orbit. With its retirement, NASA faced a fundamental problem. How do you send astronauts, heavy cargo, and life support systems into deep space without a heavy-lift rocket? For years, the United States lacked the capability to launch humans beyond Earth orbit. That gap forced NASA to rethink its entire exploration strategy. Before the SLS existed, NASA attempted another solution. The Constellation program was meant to replace the shuttle and return astronauts to the moon using entirely new rockets. However, Constellation suffered from rising costs, shifting political priorities, and unrealistic timelines. Eventually, the program was cancelled, leaving NASA without a clear path forward. What followed was not just a technical challenge, but a political and strategic one. The United States needed a rocket that could be built quickly, safely, and with technology that Congress and NASA already trusted. This is where the Space Launch System was born. Instead of designing a rocket from the ground up, NASA made a controversial decision: reuse proven space shuttle technology. The philosophy was simple: reduce risk by building with hardware that had already flown successfully for decades. It was like constructing a new deep space vehicle using engines and systems that had already survived the harsh realities of spaceflight. This choice shaped every aspect of the SLS design. At the heart of the SLS is its massive core stage, a structure taller than a 20-story building. This core stage is powered by 4 RS-25 engines, the same engines that once launched space shuttles into orbit. These engines are among the most efficient liquid-fuel rocket engines ever built. Each one produces enormous thrust while maintaining exceptional reliability. Developing a brand new engine would have taken years and billions of dollars. By reusing the RS-25, NASA gained a powerful, flight-proven foundation for deep space missions. But engines alone are not enough to lift a rocket of this size. To escape Earth's gravity, the SLS relies on 2 massive solid rocket boosters attached to its sides. These boosters are an evolution of the shuttle's original design, expanded from 4 segments to 5. During the first 2 minutes of flight, they provide more than 75% of the rocket's total thrust. This initial power is what tears the vehicle away from Earth, pushing it through the atmosphere with overwhelming force. Once the boosters separate, the core stage continues firing, carrying the mission toward orbit. Above it sits the upper stage, responsible for the final push into deep space. In early missions, this role is handled by the interim cryogenic propulsion stage, powered by an RL-10 engine, another veteran of spaceflight with decades of reliability. Its task is precise and unforgiving: send the Orion spacecraft onto a perfect trajectory toward the moon. What truly sets the SLS apart is its payload capacity. In its Block 1 configuration, it can send more than 27 metric tons directly toward the moon. Future versions are designed to lift even more, eventually surpassing 46 metric tons. This capability allows NASA to launch large spacecraft, habitats, and cargo in a single mission, something smaller commercial rockets simply cannot do without complex assembly and orbit. However, the SLS has never been free from controversy. Its development has faced delays, budget overruns, and intense public scrutiny. Critics argue that the rocket is too expensive and relies too heavily on old technology. Supporters counter that reliability matters more than novelty when human lives are at stake. Deep space missions offer no room for failure, and every component of the SLS is designed with safety margins earned through decades of experience. The debate reached a turning point in November 2022 with the launch of Artemis I. This uncrewed mission sent the Orion spacecraft farther from Earth than any human-rated vehicle had ever traveled. The SLS performed as designed, delivering raw power, stability, and precision. Artemis then proved that the rocket was not just theoretical, it was real, functional, and capable of supporting future crewed missions. The Space Launch System is now the backbone of the Artemis program, NASA's plan to establish a sustained human presence on the Moon. Artemis II will carry astronauts around the Moon, while Artemis III aims to return humans to the lunar surface. Beyond that, the SLS is intended to support missions to lunar orbit, deep space infrastructure, and eventually Mars. In the end, the SLS represents more than a rocket. It represents a strategic choice about how humanity explores space. It favors reliability over speed, proven engineering over experimental shortcuts, and long-term capability over quick wins. Whether history judges it as a necessary bridge or an expensive detour, one thing is certain: the Space Launch System is redefining how far and how safely humans can travel beyond Earth. If you want to explore the machines, technologies, and decisions shaping the future of space exploration, subscribe to Steel Wings and Iron Seas, because the next giant leap is already underway, and this time it's built to go further than ever before.